Welcome to another episode of the Arjun Kimani podcast. This episode is a bit unusual as I have a co-host with me, Sam Kuypers, who is a theoretical physicist specializing in the foundations of quantum theory and time. Our guest today is Julian Barbour, author of The End of Time and The Janus Point. Gentlemen, thanks a lot for joining me.
Thanks for having us. Thanks for having me, and thanks, Julian, for coming on.
I'm not going to lie, it is a bit intimidating sitting here with two experts on who've explored the physics of time in such depth and breadth. Well, I don't even have a high school degree. I guess it just goes to show the increasing irrelevance of credentialism. And I think the internet really levels the playing field, right? Here I am sitting in my bedroom at my parents' house with a couple of physicists who probably know as much about time as anyone on the planet right now. So having said that, I'm going to let Sam kick things off with some questions for Julian. I expect him to lead much of the discussion today, and I'll jump in if we get too deep into the weeds of physics, since I'm a novice in that area and imagine much of my audience is too. So, Sam, over to you.
Thanks. So Julian, thanks for coming on. It's great chatting with you again. So we have a shared interest in time, in timeless theories of physics, and I think it would be nice to maybe explain, first of all, what that means. So, for example, the phrase timeless physics or time without time is sometimes used, and I think it can be a bit confusing because it sounds like a contradiction. And could you perhaps explain what is meant with that?
Yes. Now, my feeling, I would say that instants of time exist, and I would now say that they are shapes of the whole universe, and in any instant we are in one of them. But there's also the notion of duration. I would say that duration between instants is not something that is out there in the world. It is something that we put between instants to make sense of them, and that can be shown mathematically to make sense. You can imagine just taking a whole lot of photographs of what the world looks like, and each of them would be somewhat different from the others. And then you could imagine there is a way, and it can be laid out mathematically very precisely, that you can lay them out in a particular order with separations between them, so that they seem to unfold in the most uniform way possible. This is a notion which the astronomers actually introduced called ephemeris time when they started having doubts about the rotation of the Earth, whether it was a good clock. And so that can be laid out mathematically with considerable precision, I would say. So at least at the level of classical physics, that's what one can do. And it's not that dissimilar from a movie film. You can cut up the slides of a movie film. They're all, if it's an ordinary film about a usual love story or something, they do follow each other more or less continuously. Each one is slightly different from the others. You can cut up the whole movie reel into individual stills, but then you can put them together again by the content. So for me, the absolute critical thing is always the content within a shape.
Right. Would it be fair to say, kind of metaphorically, that there's the instance of time and then there's the laws of physics, which are like the glue between them? Like we can reorder, or from an unordered set of these instants, we can kind of reorder them again because of the laws of physics that exist.
I'm not so sure that I would call it glue. I would just say, a very important thing is the assumption that the actual ones that unfold or describe the universe, there's a continuity between them. That one follows continuously after the other. That's not really the case with a movie film when you cut the slides. It's the continuity which enables you unambiguously to say this one follows another. At least it does, except in rather bizarre situations. And then on top of that, I would say the continuity will enable you to arrange them in an order. it's then the spacing between that then you invoke a law of nature to do that.
Right. It's maybe to use a little anecdote. I recently went to Portugal and saw a little house there that was not very well taken care of. And I just remember thinking about, I've been reading the End of Time and Janus point again, and I remember thinking, well, it's quite striking that I've never seen this house before. And I know that there is a kind of a story here. I know that there was something happened, like people neglected it. The chairs and tables were kind of, they had, they were falling apart, and there were plants growing everywhere. And I thought it's quite interesting that looking at this right now, logically, it could just be that houses appear like this out of nowhere. But we know from our explanations of the world that such things don't happen, that kind of looking at the state of the house as it is right now, it kind of implies that things have happened to it, which reminded me of your phrase that time is in the instant. So there's something in that instant which implies that time has happened, or that time has passed. Is that another? I don't know. I was wondering if you would agree with that. Again, it's kind of to
absolutely no. I mean, to quote myself in full, I say, the instant is not in time. Time is in the instant, and it's the evidence for what we call time is in the instant. But that brings me on to what I think is a really incredible thing about the universe, which is that in one single instant, just one shape of the universe, it seems to encode the whole history of the universe and the laws that govern it. I mean, this is a very remarkable fact. I call this a time capsule. And I think it first really became significant with the development of geology in the middle of the 18th century, because scientists started looking at the surface of the Earth and saying, no way could this have been created 6,000 years ago, as the book of Genesis says. What we see on the surface of the Earth can only have come into existence through the effect of laws of physics, physical processes acting through time. And Lamarck, the precursor of Darwin as an evolutionist, the one who said that giraffes get longer necks, or their children get longer, their offspring get longer necks because they pass on the fact they've been stretching up, catch leaves. Lamarck has this saying, which I absolutely think is wonderful. He says the surface of the Earth is its own historian. And I'm still working to try and develop a theory of the universe which really shows that how it can be that we experience a shape that is of this nature, and I mean our whole experience is of this, because I remember very clearly the first time you came to my house, Sam, and our various discussions in between. While that's all in my own head at the moment, and I can call that up. That's an extraordinary, rich, consistent network of, we call them records, we can't find any other word for it, but it's all there. That's a pretty amazing thing that the universe is like that. So the question is, how does that come about? We might get onto that a bit later. But I mean, there is this saying, to see eternity in a grain of sand. Well, I mean, scientists do that now. They look at a grain of sand in an electron microscope, and if they're trained scientists, they can see the evidence for how the various atoms and molecules were created over, millions, trillions, billions of years.
Yes. Yeah, that's a very nice quote. I guess also to clarify some other concepts. So one of the things that the timeless or relational theories of time are kind of in opposition of is this sense of absolute time. So Newton's view of time was that it's this thing that's ticking away uniformly everywhere in the universe all at once. And, excuse me, it's kind of a time that's outside of the universe. It's like a thing which isn't really evident from anything we see. It's just invoked as a thing that exists out there. And it's not clear how it's physical. And everything that you're saying is we don't need that kind of view of time. Time exists within the universe. Time exists within this moment. We, as you were saying, there's records of the past. There is memories of the past that we have. There's things which imply that processes have been bringing about certain landscapes on the Earth, which imply duration. So I don't know. I think it's interesting for people who don't really know about Newton's view to also see the opposing view, the thing that, in some sense, you're attacking, or the thing that we want to do away with.
Yes. Now Newton, I think, very early on, I mean, as in his early 20s, had somehow got into his head, first of all, that space is infinite. I try and describe Newton's absolute space as a great block of translucent ice, which extends to infinity in all directions. And Newton then employed this thing. I mean, on a real block of ice, you can scratch a straight line. And that was critical for Newton to talk about inertial motion, that a body left to itself will move in a straight line. And then he said, and at a uniform speed. But it's very interesting if you read what he says about absolute time in his famous Principia, published in 1687. He gives examples of actual motions. And for example, that the astronomers know that the natural day, which is determined by where the sun is in the sky, does not match up with where the stars are, because the sun is moving relative to the stars around the ecliptic at a variable rate. So already back in Ptolemy's time, in the first 2 centuries, 150 of the modern era, Ptolemy had declared that it's sidereal time. It's the time told when a particular star is due south. That's what tells that the one day has been completed. And Newton acknowledges that, and then he goes on to say that recent experiments with pendula that the astronomer Royal Flamsteed had made at the Greenwich Observatory had confirmed that pendula keep time with sidereal time. So Newton was well aware of what the evidence for time was, but he seems to have had this such visceral belief in uniform things and absolute things that he just sort of introduced these things. And then I would say, it had a very perverse effect. We might get onto that in the further development of physics in the following centuries, because these seem such clear concepts. It was very reassuring to work with them. But in the end, I think they're very wrong.
Nice. Yeah. So again, for maybe the more of the layman audience, that is the view of time which both of us really would like to do away with. We would like to say there is no such absolute time. There's no absolute space. There is only space relative to, or position relative to, other objects in the universe, not to some kind of ruler outside of it. And when we say things like there's time without time, what we really mean there's no absolute time in Newton's sense, but there is still time within the universe. There's still relational time. There is this notion of time that you've been talking about the instants that seem to continuously follow each other up.
So one
anyway,
question: does Newton's theory still make sense, or is it at least internally consistent if you remove the abstraction of time?
In fact, I'm in the midst of writing quite a long paper about this. So Newton, and I've been very influenced by the great French mathematician Henri Poincaré, who said we really should keep Newton's second law. Newton's second law of motion tells you how forces change motions, but he argues against Newton's notions of absolute space and time. But he doesn't. He does that in different places and doesn't put together a complete coherent story. Now, what I'm now saying is that Newton contaminated the inner core of his theory, I would say, is his second law of motion, acting on bodies that are subject to forces in the universe, but that he contaminated the true core of his theory by introducing the notion of absolute time, absolute space, and with absolute space comes the notion of absolute scale, that, as Sam has already said, that there's a ruler outside the universe, that I can measure the width of your face on this thing. Well, it comes out at a bit over 2 centimeters when I do that. And that, I think, really contaminated Newton's theory and disguised what a wonderfully creative theory it is. If anybody wants to check out and look on the archive, there's a paper by me with the title "Gravity's Creative Core," which anticipates the paper that I'm currently writing and hope to put out in a few months. By the time perhaps people are looking at this, it will be out there. Look out for my name, and the title at the moment is First Principle Hints of an Alternative Cosmological Paradigm. But what is really dramatic is, I find, when you take away the absolute ruler, and we might get on to some of the extraordinary things that show up when that is done. Anyway, I hope that helps. But I think, well, let me just say, there was this famous debate almost immediately after Newton published his great Principia between him and Leibniz about the nature of space and time. And I think that if you take Leibniz seriously and do what I've just been saying, remove all the contaminants that Newton put on top of his own beautiful theory, there will be a wonderful reconciliation of Leibniz and Newton, because then you see that Newton's theory is absolutely incredibly creative. And I will be able to show 1 or 2 slides which will illustrate that in a bit later. So it would be a very nice reconciliation if that really comes to pass.
I thought that you already had such a theory. I thought that, for example, shape dynamics is kind of that already, where you remove the various contaminants, as you call them, from Newtonian dynamics.
Yes, that's quite true, but it's only very recently that I've realized quite how incredibly far that goes. When you really take it seriously, it's taking out absolute scale has a much bigger impact than I realized. But we'll come on to that, and I think I've got slides which I'll get you to show them, because I'm not very digitally savvy, and I like to get other people to handle the sharing screen.
So sorry, would you like us to, because I still had questions about shape dynamics and because you mentioned shapes already, you mentioned the shape of the universe and its importance. And I was curious if you wanted to elaborate on that now, or do you mean that you want to keep that for in a moment?
No, I think it's very good to get it now. So it's very easy to get the key idea of shape dynamics. Suppose there were only just 3 particles in the universe, a universe of 3 particles. Well, they would always form a triangle. It's in Euclidean space, so the internal angles of the triangle would add up to 180 degrees. Now, normally, when you think about a triangle, you think that it has both a shape and a size. Now, the shape cannot be changed because those angles just add up to 180 degrees. But the size will change if I have as you see my hand, as I move my hand backwards and forwards, you see it getting larger and smaller. And exactly the same would happen with a triangle. So really, you'd say the size should not come into the description of the universe at all. It should only be the shape. So this was what led me to coin the expression shape dynamics. Sometime I was starting to use that in talks I was giving in about 1997, so a bit over 25 years ago. And I think it first appeared in a paper of mine in about 2003. And also I have the concept of shape space. So again, in the case of a universe which just consists of three particles, it's just all possible shapes that those particles would form. Now, what's rather wonderful, Newton was the person who introduced the notion of mass. It's surprising how late the notion of mass introduced. So you can associate different masses with particles. So they can all have the same mass, or there can be mass ratios. So let me also say that I think nothing in physics should be allowed unless it's a ratio. So the internal angles of a triangle are determined by the ratios of the sides. So that's what I would say. That's kosher. That's on a sure foundation. That's honest. So I even jokingly say my children should inscribe on my gravestone, "Nothing without ratios," because it's extraordinary how that gets forgotten. And people think that, when people think that, when people say the universe is expanding, a lot of them have, I would say frankly, a pretty naive imagination that my universe made of three particles, the size is increasing. What I would say is really happening is the shape is changing, and then so you would then get a triangle which it might start off being equilateral, but then would become more pointed, and then you would, in each case, you would have to take one of the sides of the triangle to be your ruler to measure the length of the other two. So if it's an equilateral triangle, they will all have, their length will be one. But as it gets more pointed, you would take the shortest side to measure the other ones. And then you would say that I would call that the intrinsic size of the universe, it gets greater. And that is really what is happening with the expansion of the universe, because on the most large macroscopic scale, the typical diameters, galactic diameters, the ratios of those diameters stay more or less constant, but the separations between the galaxies is increasing. So that is really what objectively the expansion of the universe means. But it's amazing how many people, even cosmologists, forget that. So I distinguish between an intrinsic size and an extrinsic size, which you have to imagine that's a ruler outside the universe to measure. So that's the key difference between what I say and the sort of the Newtonian way of thinking about it.
Yeah, I like that example. That the triangle has its own ruler built into it because the different sides can be used to give a notion of relative size, which is nice.
Yes, I like it. I've just come in, Sam. We have this further sense beyond sort of sight and touch. We have this sense which is called proprioception, where in any instant we're aware of the relative disposition, the relative positions of all our body parts. You know, I before banging my knees together, I can tell that they're very close to each other. And I like to think of the universe also having proprioception. Well, we are part of the universe, and we certainly have proprioception. And so if the universe is aware of itself, let's suppose that it is, then it will understand its expansion, that it's expanding in exactly the same way I said. So that there is a precise quantity which I can quantify that by, which perhaps we might come on to that. What do you think, Sam?
Yeah, I mean, yes. Sounds interesting.
So the way I come to this is, suppose, well, first of all, let me make a general comment which comes from reading Leibniz. If anybody's watching them, I do recommend them to read. Get hold of a nice book of Leibniz's philosophical writings if they're interested, because Leibniz is a really fantastic thinker. Kurt Gödel, who was one of the great mathematicians of the 20th century, rated Leibniz extremely high. And Leibniz just makes the blindingly obvious point that if there were no variety in the world, there was nothing. There would be nothing. We couldn't say anything. We wouldn't know anything. There would literally be nothing without variety. And this made a big impression on me. So I was always on the lookout for something that measures variety. So now suppose you have a large number of particles in Euclidean space. Is there a number, a pure number, which measures the extent to which they are clustered or uniformly distributed? And I want that number not to depend on this wretched external ruler. So it's got to be what one says is scale invariant. So to be scale invariant, the most obvious way to achieve that is to take two quantities which are lengths and take their ratio. And there's two numbers which stand out as being very obvious. So let's assume all the particles have the same mass, but it's quite easy to add masses. So there's a quantity called the root mean square length. So what you do, you take all the separations. You imagine there is a ruler. You take all the separation between the particles. So for each pair of particles, you square that separation. So you add up all those squared separations and take the square root of it. And that's called the root mean square length. And then there's another length, which is called the mean harmonic length. And that actually, very intriguingly, it is the inverse of Newton's gravitational potential. So Newton's gravitational potential between two particles, you multiply the masses, but if the masses are all equal, that just makes one. But you divide it by the distance between them. That's the gravitational potential. And then the force is derived from that. It's 1 over the square of the distance. So the mean harmonic length, to find that, you add up all those 1 over r numbers, and then you invert it, and that's the mean harmonic length. And so then you divide the root mean square length by the mean harmonic length, and you get something which my collaborators and I call the complexity. It's a pure number, and it has very, very remarkable properties which haven't really been properly noticed hitherto. Shall I stop at this point in case you sort of come in with questions?
Yeah, I was trying to understand how your point about variety relates to this, because with the Big Bang, there was like this initial burst of creativity in the universe, and everything from like atoms to the first stars to first galaxies, they formed, and then after about like 400 million years, no fundamentally new astronomical objects arrived in the cosmos. And I think like from that period to the period of the genesis of life on Earth, that is what David Deutsch calls the great monotony. And then obviously with life and this with adaptations that could create knowledge, and then that could be encoded for knowledge. And then with humans, obviously, we're like kind of the ultimate source of novelty in the universe, and basically the antithesis of the universe is bland monotony. So, but I'm just curious how your point about variety fits into this, and if you think.
Well, yes, good you raise it. Now, I think this is the point to talk about a very remarkable mathematical discovery that was made in 1907 by a Finnish mathematician called Carl Sundman. So he was considering Isaac Newton's theory of point particles interacting through gravity, universal gravity. And he was the first person to ask, is it possible for those three particles to collide all at once? This is in the Newtonian way of thinking, so that in the Newtonian picture, they would all collide at once. And he showed that they could. And it's a very profound mathematical bit of mathematical work. but the very interesting, he showed some very, very interesting things about it. First of all, he showed that the overall angular momentum, the overall rotation in the system must be exactly zero. Next, he showed that as the particles are coming to collide together, the ratios of the separations between the particles must all tend to the same value. So, and there was only two ways in which that could happen. The more interesting one is that as they get together, the shape becomes that of an equilateral triangle. And that means that so the ratios of the sides in that case all tend to 1. So if there's many more particles, they won't all be tending to 1, but they'll all be tending to some ratio. So that's a very interesting result. So that's one thing when it becomes an equilateral triangle. And the other one is when it's all laid out on a line, the three particles on a line, and one is between the other two. Now, those situations are, well, first of all, it's a very extraordinary result. And only a year later, another mathematician called Bloch showed that exactly the same thing, it could happen with any arbitrary number of particles. An arbitrary number could all collide at once. But they would, the final shape had to be very special. Now there's a huge number of shapes, and I'll be able to show you some of them, what they look like in a moment. But what is remarkable, well, there's several very remarkable things about this. This was happening 1907, 1908, 9. And it's only 20 years later that Hubble is getting the evidence that the universe is expanding. But now, so basically what those mathematicians found and thought was that they'd got particles all colliding at a point. But Newton's laws allow you to, they're said to be time reversal invariant. You can just run it backwards and they still obey Newton's laws. So what that means is that mathematically they discovered a Newtonian Big Bang. All the particles, now the normal way people would think about it is all the particles explode out of a point. But that's not the way to think about it. The first instant of time in the three-body problem, where you've just got three particles, is an equilateral triangle. That is literally the first instant of time in that universe. And from then on, the shape just changes and gets more. So what happens then in that case is that as the system changes from being equilateral, two particles will get trapped and start going around each other in ellipses, in Keplerian ellipses, while the third particle goes off in the opposite direction. So out of that complete uniformity of the equilateral triangle, you get structure forming and order forming. Now, there's all sorts of interesting things about that. First of all, this is an extraordinary new way to think about time. It is literally saying Newton's laws are telling you when, and because what's happened here is you've got rid of all those absolutes of Newton. All of this is governed by that quantity I just defined, the shape complexity. That is actually what is governing things, and that comes to the shape complexity can have an absolute minimum, it can have local minima, or it can have saddle points. And these total collisions can only happen at these critical points, either minima, local minima, or saddles. And so this is pure mathematics, but it's mathematics about variety, and it's saying very, very profound things about time, how structure forms. I don't know how much more one wants. It's pretty amazing. And that all came out of, and that's all hidden. That was all hidden for several hundred, since, 1687 through to 1907, over 200 years. This incredible secret was hidden in Newton's theory of gravity. And and you really it's revealed. It's a bit like I would say Leibniz came along and say, take away those curtains hiding the truth. The curtains were these absolute things that Newton imposed on his own theory. He locked it up in a box in a way, and hid all the wonderful things that are going on. So it's a pretty amazing story. And if you have enough particles and you give them different masses, and by the way, you can also introduce things like electrostatic forces and other types of forces, that the same sort of thing will happen, but we haven't worked out the details on that. So that's what comes out of it. We might, I don't know, do you want to ask some questions? Then I would suggest we look at one or two of the slides, if you feel. But Sam, do you want to make any comments or ask anything first?
Well, I definitely agree that it's very profound what you found in Newtonian mechanics. I mean, it's both the research that you were alluding to earlier that's happened in the last century, and also your own investigation of the theory shows it's much richer than at least I ever thought it would be. As I said in the past, I used to think that I kind of understood Newtonian mechanics pretty well, having done high school and undergraduate courses on the topic. And you think, well, there's probably not that much more to know about Newtonian mechanics, and I was profoundly wrong, which I realized when I was reading your paper, The Nature of Time. And so that's quite profound, and it is quite profound that the universe gives rise to structure. That, as you said, you can start with an equilateral triangle, which is completely uniform, and then from that structure emerges, which is also completely unintuitive in many ways. And
yes, carry on, sir.
Yeah, my question was going to be that lots of the other structure you see in the world is, of course, it's electrostatic, or it's due to electromagnetism and the weak and strong nuclear forces, and things like atoms, which are structures as well. And their formation is explained by quantum theory. So I was wondering what you think of that. Do we need quantum theory to explain the structure of the world?
Well, yeah, this is very. I tell you what, though, shall we perhaps look at one or two of the slides?
Let's do that. We've been promising the audience.
I would suggest that the one to show first is the one that's called Batty Together. So this is 5,000 particles in Euclidean space, and this is at the either at or very, very close to the absolute minimum of that quantity that I defined, the complexity. And you see, it's an incredibly perfect sphere and a very uniform density. And this is another wonderful thing about Newton's theorem. It has this structure because of Newton's potential theorem. So Newton's potential theorem explains why celestial bodies, if they're not rotating, like the sun or the moon or the earth, are spherical. So basically, if you're outside a spherically symmetric distribution of mass in Newton's theory, it's the gravitational force that you feel is exactly the same as if all the mass is concentrated at the center at one single point. And if you're inside that distribution, the force you feel is if the mass that is within the radius at which you are is concentrated at the center. And I won't attempt to go into the full mathematics to explain what that is, but this is what is behind this incredibly uniform structure that you see here. In fact, de facto, there's two forces really at work when you look at it well. There's Newton's gravitational force pulling everything towards the common center of mass, where there would be what's called a total collision. But it's stopped from happening by there being effectively repulsive forces, hook forces, which increase with the distance from the center. And that's what's holding it in balance. this is a very, very remarkable and wonderful property in Newtonian theory, which I guess has, well, it was beginning to become clear in the start of the 20th century, but these numerical calculations show just how amazing it really is. So basically, these calculations, which were made by Richard Batty and kindly passed on to my collaborator Flavio McCarty, that they were calculations made in a paper published in 2002. So pure mathematicians had long known that you would get something like this, but these are numerical calculations that show it. Now, what then happened was nobody had really thought. So there's a huge number of these shapes. They're called central configurations because if there was only the gravitational force and the particles started at rest, they will fall under gravity and all collide at the center of mass. By the way, I forgot to say, of course, the one on the right in this image here is an equatorial slice through the one on the left. Let me just recall where I got to. Yes. So it had been clear to theoreticians that you would get something like this. So now there's a vast number of these things. If you have 5,000 particles, the number of these special shapes, they're called central configurations, is essentially factorial 5,000. So that's 5,000 times 4,999, all the way down to 1. So just imagine how many there are out there. It's just incredible. But then this is a very nice thing. So I've been interacting with very good mathematician specialists in Newtonian theory. By the way, there's about sort of 50, I guess, real specialists in Newtonian theory who work on the really fascinating and foundational issues in Newtonian theory. And that goes beyond, as Sam was saying, anything that you would have learned at university, unfortunately, because it's very wonderful. So one of the professors at the observatory in Paris had a student, Manuel Izquierdo, and asked him to find some more of these things called central configurations. So can we go on to, this is a calculation done in 2 dimensions, and you already see that in 2 dimensions, Newton's theorem doesn't hold, because on the left, you've got this is 1,000 particles in 2 dimensions, that's a central configuration, and you see that the separation between the particles gets greater as you go to the edge. Now, what Manuel did, Manuel Izquierdo, for some reason, he wrote a program which found these central configurations at not very, very close to the absolute minimum, which previously everybody else had tried to do, but at somewhat above. And then he found these extraordinary things, which you see on the right there. This is the complexity. It's a pure number. It's only about, I think it's about 3% greater than the one on the left. But suddenly, out of nowhere, incredible structure, these filaments, voids, loops with different numbers of particles inside. So that's 1,000. And, there's just huge numbers of these things sitting out there in Newton's theory. So in some ways, I would say that there is a theory of creation in Newton's theory. You define this quantity, which we call complexity. It's a measure of clustering or a measure of variety. It's something to quantify how much structure in the universe there is, and you ask for its absolute minimum, and you find it's incredibly uniform. And then you say, I want a bit more variety. What's it going to look like if we take Newton's theory? And lo and behold, look how the structure comes. So I would say that Newton's theory, properly understood, is a theory of creation. So it's rather interesting. What is the etymology of creation? Where does that word come from? It's an Indo-Germanic word KER, meaning to grow, which is very appropriate. It's nothing what to do with creation out of nothing, creatio ex nihilo. It's to grow. So this is exactly what you see there. So Newton's theory is a theory of growth, of creation understood in that sense.
And the complexity is not bounded, right? It's a quantity that can keep growing forever.
It goes forever, yes. And you can let the number of particles increase as much as you like. So you can go to infinity with that, and I suspect you will get ever richer structures, particularly in 3 dimensions. And as I say, I think you can bring in more forces. Then also you can, with my main collaborator Tim Kozlowski, we're working on the idea of not just of getting ever closer to infinity just by increasing the number of particles, but actually imagining that you have an infinite number of that there's an actual infinity in space. And then we think this might lead to a theory of creation. This is very speculative, but a theory of creation that goes on and goes on getting forever richer and richer, because if you have infinitely many particles, the number of combinations is infinitely you can't stop. There's infinitely many combinations that are possible. So this is look at the structures here. This is 100 particles in 2 dimensions. So this has a very interesting structure, which is still not understood. Because it's in 2 dimensions, look at the red particles in that filament in the center. You'll see that except at the edge, the separations are all more or less equal. And then towards the edge, they get bigger. That's because it's in 2 dimensions. And then you see, but there's a whole hierarchy of filaments. The next one is the orange one. So you see there's 3 orange filaments. There's a sort of about just under half of a circle just to the right. Then there's an arch above the center. Then there's one going down to the right. Then there are green filaments just consisting of 3 particles. You can see them in the bottom left quadrant. And then you see there are yellow ones that are further apart. And then you see ones that are just scattered, which are even further apart. So this is pretty rich structure out there. And all of this is a discovery made only about just over 3 years ago at the observatory in Paris by Manuel Escuerdo.
And this is in 2 dimensions, so it's because before you showed us
2 dimensions. And I mean, one of the things I'm really hoping is to get somebody with supercomputers and really get analyzing what happens with many more particles, introducing more forces. I mean, they don't rule out that we could do what quantum mechanics does, which explains the shapes of molecules. I mean, you know, these sort of dumbbell images of molecules where the quantum mechanical explanation is that these atoms are swapping electrons, isn't it, between each other that create the binding. Am I right there, Sam? I think I am. And and that's so you have these. They're depicted as sort of dumbbells with a rod connecting them, which is the electron thing. But suppose we find when we put electrostatic forces in as well, that we just find structures like that emerging. Isn't that beginning to put a question mark over quantum mechanics? So now, if you have just 3 particles, the shape is determined by 2 internal angles, so that you can represent the shape of the triangle by points on the surface of a sphere called the shape sphere. This is something that was introduced by people working on Newtonian theory about 30, 40 years ago. So basically what you're seeing here is the white curves are the values of the complexity, that quantity that I characterized. This is for three particles of equal masses. So the absolute minimum of the complexity is at the poles. Mirror triangles that are mirror images of each other have the same longitude and opposite latitude, and the degenerate triangles, which are all on a line, three particles on a line, the collinear ones, they are on the equator. So there are three special points called Euler configurations, because Euler actually discovered them, and I'll say something about them in a minute. So an Euler configuration is the one just left of the center of that vertical line there. So there's three Euler configurations, and then there are 3 points in the, you see one where it goes deep mauve, where two particles are very close to each other compared with the distance to the third. So that if you divided the distance to the third by the separation between the particles, it would go to infinity. So that's when the complexity becomes an infinitely high mountain peak, high pointed peak, goes right up there. Now, it's worth saying something about this Euler configuration. So Euler was the first person who discovered these remarkable central configurations, although the name was only coined in 1899. So what he showed, what Euler showed, was that if the moon was 4 times further from the Earth than it is now, and was 4 times further from the Earth than it is now, the Earth and the Moon, if they were on the same line as the Sun, the Earth and the Moon could all go around the Sun, revolve around the Sun, keeping in a straight line. And on the Earth, we would see the Moon, full Moon, always, and but only with a quarter of the diameter. That was the first central configuration that was found. But so the interesting thing about that is that the particles, in that case, the Moon and the Earth do not fall to the Sun. They don't all fall together because of centrifugal force. That's a force that increases with the distance increases with the distance, and that's what keeps it in balance. And the most beautiful example of that altogether in the heavens is Saturn's rings. Saturn's rings are a central configuration, and they are prevented from collapsing by centrifugal force, which happens in 2 dimensions. So that's where the 2 dimensions come into their own. And so that's it there. Then about 10 years later, Lagrange showed that an equilateral triangle is also, that's the one that Sundman plays such a central role in Sundman's paper from 1907. Lagrange showed that in 1772, whatever the masses of the particles, that's an exceptional case, whatever the masses of the particles, they could go around, they could orbit stably. So at one of the vertices, you would have the Sun, and another you could have Jupiter, and at the third you could have an asteroid, which is always forming an equilateral triangle with the Sun and Jupiter. Lagrange didn't think of that, but somebody later did, and looked to see if there were any asteroids either going ahead of Jupiter or behind. And indeed, they are out there, and they're called the Trojan asteroids. So that's very interesting. So this is all intimately related. Now, if there's anything that people, when they learn about Newtonian gravity, they might just learn about that. These special things are called Lagrange points. So the moon would be at what's called L2. And in fact, the the Space Telescope, the James Webb Space Telescope, is now sitting at what's called L2. So the James Webb Telescope is on a straight line always from the sun through the Earth out to the James Webb Telescope. And my friend Alain Albuy, that professor at the observatory in Paris, drew my attention to a remarkable coincidence. So from the Earth, the moon and the sun have about the same apparent diameter. And that's why we have these very spectacular eclipses of the sun. But then equally remarkable, from L2, where the James Webb Telescope is sitting, the Earth and the sun have about the same diameter, apparent diameter. And that's why there's a shadow cone in which the James Webb Telescope sits, that it's quite small. So telescopes that have been put out there, every now and then they have to maneuver them a bit to keep them in the shadow so that they keep nice and cool. So this is all a very beautiful illustration of these things. So this is probably, I would think, most people who know about Newtonian gravity, that's probably about the only part of this really wonderful, deep truths and facts about Newtonian gravity that people generally will know about, if at all.
We could also talk about special and general relativity. If I'm curious how you think about those theories, because you do mention them in The End of Time, for example, that you also have a relational or more relational version of general relativity, for example. And shape dynamics itself is also kind of an attempt to replace some of what we see in general relativity. So as I understand it, shape dynamics is able to approximate space-times that, for example, don't include closed time-like curves. And I think, Julian, you would say it gives a more physical interpretation of what's going on in general relativity. So these are really two questions: is general relativity in of itself and what you've done on that theory, and also shape dynamics and how it relates to general relativity.
Yeah, but yes, that's great. Now, I got into all of this purely by chance back in 1963 when I read about the one popular science article that Paul Dirac, the great quantum physicist, had ever written, and it appeared in the Scientific American in May 1963. And in it, he reported his analysis of the dynamical structure of general relativity, not treated as a space-time theory, but as a Hamiltonian theory, a dynamical theory, as a preparation to make a quantum theory of gravity. And he said he was very surprised because he found that if you wanted to make a quantum theory, you must get rid of all redundant bits of information, gauge degrees of freedom. So in space-time, normally you think of it like being a loaf of bread, which you can slice in many different ways and define simultaneity in many different ways. And Dirac said, this is just introducing redundant information. That's not really in the dynamical core. That's not really what is driving general relativity. And he said, really, to eliminate everything that is redundant, this is sort of Occam's razor, you have to restore simultaneity. At least he felt that was the only way that you would ever be able to create a satisfactory quantum theory. And he very emphatically said, first in 1958 when he did that work, and then a year later when he published another paper related to it, he emphasized repeatedly that he said, I'm inclined to believe that four-dimensional symmetry is not a fundamental feature of the physical world. And when I read about that, the next day I woke up and said, well, if Dirac doesn't believe in simultaneity as a fundamental feature of the physical world, what is time? So that's what started me off on all of these things. And I think it's true to say, now I've got here a little thing that I illustrate with triangles. You can see that's coming across, is it, fairly well in the thing. So this is my idea of just with three particles where I've arranged them sort of following each other. So this would be the universe. This would be the shape of the universe. This triangle would represent the shape of the universe at its successive instants. And that's really, I think, how Dirac was saying we should think about general relativity. It's about how the shape, although he didn't use that expression. In fact, I don't think he was thinking about taking the scale out. He was just thinking of the configuration. You should think of it that way. And basically, I would say that's what my collaborators and I have done. But we've also relied on, first of all, there was Dirac did that. But then there's very important work was done about 12 years later by Jimmy York in America, and his student at that time, his first PhD student, Nilo Muracho, the Irishman. And they worked on what's called the initial value problem in general relativity. Now, in Maxwell's theory, you can't just specify initial conditions as you like and then evolve them and see what happens. You can do that in Newtonian theory. You can specify initial conditions and see what happens. In Maxwell's theory, the electric field has to satisfy a very special condition, which is called the Gauss constraint. Its divergence has to be zero in empty space, or it has to be equal to the charge density. And those are elliptical. That's an elliptic equation which holds instantaneously over the whole of space. So there's nothing about that happening through time. There's no retardation in that. Now, in general relativity, you have similar things, but it's much more complicated. First of all, there are three such constraints. These are called the linear ADM, Arnavit-Desa-Misner constraints. That they were put in form just a year or two after Dirac's papers. But then what is much more significant and profound is that there are quadratic constraints which hold at each space point. So it's a very complicated situation, and it wasn't really, well, the first way of, so you can't do anything in general relativity to find a solution, a proper solution, a non-trivial one, until you found a way to find data that satisfy those initial constraints. And that was found by York and Muracho in the early 1970s, and it's then played an important role in numerical relativity afterwards. And an account of all this is in a book, Shape Dynamics, by my collaborator Flavio Mercati, which was published a few years ago. So, and that's got a whole lot about, well, the full title is Shape Dynamics, Relativity and Relationalism. And if anybody wants to check it out, it's there. So that basically is, I would say, how I think about general relativity. So that does mean that not all solutions of general relativity are allowed, but I think nearly everybody who works on general relativity feels that it allows too many solutions. On the face of it, seems you can go back and kill your grandmother or your grandfather. Well, you can't in reality, but there are these mysterious closed time-like loops and things like that.
Yes, yeah, I'm one of the few people who might actually like them. I've written a paper about them at some point and trying to make sense of them. I feel like it is possible to make sense of closed time-like curves. I'm not sure we've succeeded yet. I definitely don't claim to have succeeded in fully understanding them. But yeah, it is tantalizing still. And it's again, it's surprising how much of general relativity, even if one would not agree that, even if you want to have the structure of general relativity as it is now, with the closed time-like curves and things in it, it's very strange and tantalizing to look at how much of general relativity is already present in Newtonian mechanics through shape dynamics. I mean, Newtonian mechanics might be misleading to call it that, because of course it has a lot more or a lot less, depending on how you look at it, structure than Newton put into it. So, but yeah, it's very strange and interesting that it looks so much like general relativity.
There is actually a very deep. I might just mention group theory here. So the way to get rid of what I was talking about, that contamination in Newtonian theory, is relies heavily on group theory. Particularly, well, rather trivially, you can move. Not too serious. You can move everything like that. You can rotate it in space, and you can increase or decrease the size. Now, those are what are called group transformations, and those transformations, if I rotate my hand like that, there's just three numbers which measure how my hand is being rotated in the 3 dimensions of space. So those are parameters. So these are groups that depend upon a finite number of parameters. So it's 3 for Newtonian translations in 3 dimensions, 3 for rotations, and 1 for overall expansion. And basically, what is happening in Newtonian theory when you get rid of all the contaminants is you're using those 3 groups to do it. And in general relativity, you're using groups in exactly the same way, but now these groups depend upon arbitrary functions, not upon just a finite number of parameters. So it's a very sophisticated thing. But I think this is the reason why, one of the reasons why Newtonian gravity is such a good approximation to general relativity, because the underlying structure is common to the 2 theories, but much more sophisticated in Einstein's.
Right. Now, I don't want to jump around topics too much, but we have some other questions relating to the Janus point that we can discuss if you're interested.
Yeah, sure.
Yes. So one of them is about the idea of entropy in a finite universe and entropy in an infinite universe. As you sometimes say, entropy in a box is something different than entropy in the real universe, because one of them is a bounded system. And I think probably for Arjen and me, it's interesting to think about that because of things like the heat death of the universe, and will there be heat death? And I believe you have all kinds of criticisms of that idea.
Now, Sadekano was this Frenchman who in 1824, at the age of 25, published an absolutely marvelous little book with the title On the Motive Power of Fire. And the aim of his book was to work out the way to make steam engines work with maximal efficiency. How would you achieve the maximum efficiency? And a very key observation that he made was that you will always lose some of the energy that you're putting into a steam engine. And you see that in the point is that the steam engine has to run continuously. So you have a steam in a cylinder which is heated up to a high temperature, and that causes it to expand and do work. You can lift a weight or you can pull water out of a mine, but then the steam is still hot, even although it's done quite a bit of work. It's got cooler, but it's still quite hot. But you've got to get it back again. And to get it back again, the only way you can do that is to cool it down. And in the very first steam engine that was invented for work in mines in 1702, I think it was, it's the Newcomb one. The thing they did that was very crude. They just threw buckets, I think, of cold water on it so that it went back again. But that meant that the heat was wasted. And this was the anticipation of what many people regard as the most fundamental law in physics, the second law of thermodynamics, that there will always be some loss of useful energy. Now, I think the thing that I'm now emphasizing in my fairly recently published book, The Janus Point, is that a steam engine stops working if the steam escapes from the cylinder. You have to have essentially a steam engine is about something which is in a box. And there was Carnot's little book led to the discovery of the first two laws of thermodynamics in 1850 by Rudolf Clausius in Germany and William Thomson, who later became Lord Kelvin in this country. So it's absolutely fabulous work. I mean, what happened in thermodynamics, the theoretical work is just wonderful. But of necessity, it was always about systems in a box. First of all, thermodynamic, the sort of phenomenological, the definition of entropy and so forth, is absolutely just wonderful work. And then the theoretical explanation of the phenomenological laws by, well, the first person who made a really major contribution was Clausius again. Then it was James Clerk Maxwell in Scotland, followed by Ludwig Boltzmann in Germany, and then Willard Gibbs in the United States. And in all of these cases, essentially, they're talking about particles, molecules, what you like, in a box. And it's quite extraordinary. I don't want to sound boastful, but I think I'm almost the first person who seriously asked, is the universe in a box? And what difference does it make if it isn't? And I think the answer is it makes a huge difference. Because in a box, if you start off, so the typical way I explain this, you start off with a box full of air, and you're able to put a little cube of ice in one corner. And bit by bit, the ice will melt and become water, and then the water will evaporate. And all the water molecules will be spread out over the whole box, and there'll be a completely uniform distribution of the water molecules, and they'll be moving in random. And that is really what heat death is thought to be like. And the notion of heat death was coined, the expression was coined in 1854 by the German Helmholtz. And that's what people have thought. And people, without batting an eyelid, they talk about the entropy of the universe and all sorts of things like that. But is it really the right way to think about it? And the only person that I found who did actually question it but only in passing in a footnote, was Boltzmann. So Boltzmann was in a famous debate in 1896 with somebody who then became a great logician, Zermelo. And a few years before that, in 1890, Henri Poincaré had proved his famous recurrence theorem. He showed, essentially, this would be for a system in a box. So mathematically, it's a system which can only explore a phase space of bounded Liouville measure, which is essentially meaning that spatially it's in a box and the momenta can't go to infinity. And Poincaré showed that in such a system, it would always return infinitely often, arbitrarily close to any previous state it had previously been in. And so Melo said, well, this shows that you cannot have entropy increasing forever in an atomistic system, because it might get up to a certain value, but then it's bound to go back again if you wait long enough, by Poincaré's theorem. And Boltzmann, just in more or less as a footnote, said, are we so sure that's the right way to think about the universe? Could it be that it explores infinite space? And what do we know about the energies that can happen? And he left it at that. And then Gibbs, who developed a beautiful theory, a probability theory, which is regarded as the deepest foundation of statistical mechanics, said, I must make a caveat. If the system can expand into infinite space, or the momenta can grow without bound, my theory will just become meaningless, because I can no longer attach any probabilistic sense to that story. And this just has not been registered by people. I haven't looked at everything that's been written on the subject, but I've looked at quite a lot of the literature on entropy and statistical mechanics. I've never seen anybody comment on it, but this came up in the discussions in this paper that I published with two collaborators in 2014, Tim Kozlowski and Flavio Mercati, where we showed that in the Newtonian n-body, so the Newtonian n-body problem, first of all, the momenta can come infinitely great if two particles get close enough to each other, but also they can expand. That quantity I defined earlier, the root mean square length, can become infinitely great. So it's completely different. And the behavior there is completely, it's as different as night and day. So what, again, this goes back to Lagrange. In 1772, Lagrange, for the three-body problem, but it was then generalized so to the n-body, he showed that in the three-body problem, if the energy is either zero or positive, in other words, it's not negative, but even if it's negative, much the same things will happen. If that condition is satisfied, then in the infinite past, the size is infinitely great, as measured by that root mean square length, then it will decrease steadily, monotonically, down to a finite value, and then it will increase again to infinity. And that was the first qualitative result found in dynamics, that you just have that one condition must be satisfied, and then every single solution satisfies that condition. And that's what I call the Janus point. Now, then what we point out in that paper in 2014, and the title is Identification of a Gravitational Arrow of Time, is that at that Janus point, the distribution of the particles is more uniform than around in the region of the Janus point. The distribution of the particles is more uniform than anywhere else, and the motions are pretty random. If there's a lot of particles, it's a pretty close approximation to a swarm of bees. But then as you go in both directions of time away from it, the system breaks up into clusters. And typically you get either single particles or two particles which form those Kepler pairs. And those Kepler pairs, through the period, the major axis, and the orientation, each Kepler pair becomes a rod, clock, and compass all in one. And then you get isolated subsystems. So you get the exact opposite of what is happening with that ice cube in a box. You get structure being created out of essentially chaos, out of disorder. So that's when I say those two situations they're as different as night and day. And moreover, there's a statistics of shapes which we haven't yet come on to. But so I would say, I mean, I think it's very remarkable. This has just not been noticed. And I think it's just a case of, well, it's all to you learn. Perhaps it may be the way one is taught. You're taught to pass exams when you study at the university, and then that gets so embedded in the way you think that you may not question it after that. So, anyways, so that's the sort of the background to the Janus Point book, which was published at the end of 2020.
Yeah, that sounds very plausible, the thing you said about exams. I can well imagine that being true. So you don't think that there will be a heat death then? Do you think that we might have endless variety, and like that's what I guess I would be interested in. I think something like that should be true.
Well, I mean, this is early in the story, but at the very least, I'm confident all of that issue of heat death should be questioned. Now, a lot of the present belief at the moment is to do with, first of all, black hole entropy, the entropy that's associated with black holes, for which certainly I think the evidence from the mathematical structure of general relativity and now the observations that are made is very strong, but now that the universe is being observed, the accelerated expansion, there is a further. So the black holes have an event horizon, but the universe as a whole, they now say, has another horizon where things are disappearing and we'll never see them anymore. So a rather gloomy story is that in the future, all we'll see is ourselves in the Andromeda Nebula, our own galaxy in the Andromeda Nebula. But this is much too early to be any confident about it. All I will say is I think this really all needs to be considered carefully, and it could be completely wrong. I mean, one thing that people just say without batting an eyelid is to find out the entropy of the observable the long-term maximal entropy of the matter that's currently in the observable universe. You just add up the entropies of all the black holes that could form. Now, that's very questionable. Now, if you have two systems, each of which has an entropy, and there is no statistical correlation between them, one of the wonderful things about entropy in that case is that you can add the entropies. You just add them. And that's to do with the way the logarithms work. But the assumption is that they are not correlated. But now, who's to say that there aren't all these correlations in the universe? I was talking about these instantaneous elliptical equations, tightly binding everything in the universe together, instantaneous action of distant elliptical things. I think it really, people should stop and think, are we so sure that these black holes in different galaxies are statistically independent of each other? I think the whole universe, I think there's a strong likelihood that the whole universe is so interconnected, you can't possibly say that one part of it is not connected to another, is not statistically related to another. So I think that's a big question mark. And at the moment, I mean, there's an extraordinary thing about cosmology, which was summed up by Martin Rees's book published 20 years or more ago, Just Six Numbers. It's an incredibly good description of the universe, which uses just 6 parameters. Basically, nobody really knows where they come from. And that there are all these mysteries of dark matter, dark energy, exactly why the slope that is not exactly 1 at the end of inflation, and there's all sorts of problems with inflation too. So I would say it's all very, very open. I think everything is there to be played for. I don't know whether anything will become totally clear while I'm still alive, but anyway, you two guys should be there to see it with luck.
I hope you will too.
Yeah.
So there is another story in the Janus point, which I liked, which is about Boltzmann and his construction to do with entropy, where this is really a version of his argument that I hadn't really heard before, that you have these statistical fluctuations in an otherwise completely stationary. It's not a universe that's stationary, but it's a universe that has maxed out its entropy. So kind of a heat death has happened, as I understand it, and then you have these statistical fluctuations which will still happen, and then within the statistical fluctuations, there's a notion of time because things will tend back to kind of the maximum entropy. Do you want to tell the whole story? Because the thing that's nice about it is this symmetry that he had built into that argument, which I was not aware of, for example, and then also how that relates to your theory of time in the Janus point, where there is, in some sense, there's a universe moving backwards in time relative to us. So I don't know. I'm curious about that story. I like it a lot. So.
Well, first of all, the Boltzmann's idea was very nice, but it was already serious doubt was cast on it in around 1930, I think it was, 29, by Arthur Eddington, when he was addressing a scientific meeting in London. He said, this idea of Boltzmann, so Boltzmann required, this was before the colossal size of the universe and all the galaxies was found. Boltzmann's fluctuation was, he thought, would be perhaps of the order of the size of the galaxy or something. And Eddington made the observation that it's far more likely that a much smaller fluctuation, just as Eddington said of me talking to you here in this room, that we are the fluctuation that's come into existence while I'm still talking to you. And then only within a year or two, Landau and and a very bright Russian student called Bronstein, is it? Anyway, they published a paper saying, well, actually, it's even more. The most probable thing is that just a single brain comes into existence, and thinks that it's the outcome of a whole history of the universe. And then that led, I think it's Sean Carroll, about 2000, 2001, to coin the expression Boltzmann brain. But the Boltzmann brains cause a lot of problem in all these ideas now about the multiverse, that there's lots of things. So they create a lot of problems to try and make sensible probabilistic statements. Now, I'm frankly not too fussed about that, because the multiverse anyway comes out of the idea that inflation goes on forever. But if inflation is not right, then maybe we don't have to worry about that. So the model of the universe I like is the one I take from Newtonian gravity, that it starts, that the first instant is maximally uniform. And there is, for a given number of particles, in virtually always there is one shape which is maximally uniform. So not surprisingly, I call that alpha. And then out of that, I just argued that I believe then that structure grows and just goes on growing, and order increases. So this is a completely opposite story. And I think it's entirely likely, and I will even stick my neck out and say I believe it's made distinctly plausible by what we know from Newtonian theory. And maybe there is something similar in general relativity, which people just haven't realized is there, because general relativity is such a much more sophisticated theory, where there's not only matter but the space that can fluctuate. Maybe that's. By the way, I may also say that there is in general relativity there is an analog of that complexity that I'm talking about. I won't go into all the details of it, but it's something called the Yamabe invariant. So there is an exact analog in general relativity of that. So maybe the way to try and understand general relativity is through this quantity, which, as I say, is analogous to the complexity in general relativity. But that's perhaps a bit too technical to go into here. So I don't know what more. I think before we end, something is worth saying about probabilities of shapes, Sam. But do you want to go first with anything else?
Well, we still had some questions. So there's two things we still have. There's some questions from people on Twitter, including from David and Brett. And we have some questions that are just
kind of philosophical philosophy stuff.
I think that would be nice. I think that would be it would be nice to go through all of those, and we don't have to make it very long. But I think each of those questions would be fun to discuss.
Yeah. So I'm curious, does your understanding of the universe and time allow for the existence of free will?
That's the $64,000 question, isn't it? I recently said to Nicholas Berg-Gruen, who wanted to talk to me about time and asked that question, I said, if I believe in anything with free will, it would probably be the universe in its totality rather than me. I don't know. I think, particularly if the universe, I was saying that the universe could be infinite. I think I can see my way now to say that the future is not, that the past doesn't determine the future uniquely. There's two reasons for that. One is to do with this very special nature of the way it starts, and also if it's infinite. So I would believe, I'm inclined to, at the moment, I'm sort of thinking in terms of a sort of a many worlds interpretation of the universe, but not in the quantum mechanical way, but that there will be there could well be many different versions of me that have the same memories, that they will all have the same sort of memories, but they will have different current experiences. And so you can do almost anything you like if you've got infinite possibilities. So the way I think about it is that the world and sort of what looks like or comes across to us as deterministic causality is emergent, but it's not exact. That you can't predict the future, but there will be circumstances when you can. I mean, the mere fact that I clicked on the link and so forth there shows that the universe is pretty coherent. But there was always a small danger that I would forget or something like that. And then you'd have been frustrated. But I mean, that's one of the reasons why I think that artificial intelligence will never really come up with wonderfully new things. It just can't draw on enough information and so forth. And the structure, I mean, it's always coordinating past structures that have been created in the past. So I don't rate. I mean, obviously, artificial intelligence can be extremely useful in many ways, but I'm not sure it's going to turn out to be so wonderfully creative.
I agree. Some people would say that the laws of physics determine everything in the future, and so we have these dynamical laws that we can apply, and they seem to point to an arrow of time which kind of arbitrarily only moves forwards, right? You can't we could in principle take that set of instances backwards in time as well, so that's like, it seems like this kind of an arbitrary way of having this forward arrow of time there, and then saying, everything's there already in the past, and the future is determined by these dynamical laws of physics.
Well, well, first of all, for the reasons I gave, I don't think you can say that the past really determines the future, only to a certain extent, under conditions which hold quite widely. But that idea of sort of running the universe backwards, which technically within Newton's laws as they stand for a finite number of particles you can, that was envisaged, I think, by the same Lord Kelvin. But I think, if I remember right, he said actually we wouldn't notice any difference. We would just think we're going forward in time. So it wouldn't change anything. I mean, the reality is out there. It's just a succession of, in my view, it's just a succession of snapshots, and each snapshot is aware of itself, as all three of us are. In any instant, we're aware of ourselves and what we know. So that's how. Go on.
Yeah, maybe on a more personal level, how has your understanding of time influenced your life philosophy or worldview?
Well, Carpe diem is the saying, the Latin one. Grasp the day, make the most of the day. I think I'm pretty good at enjoying myself. I mean, I certainly have not the slightest aspiration to go on cruise ships or anything like that. But I enjoy good food, going for a walk, listening to good music, and talking with friends and things like that. So I would say I'm pretty good at enjoying myself. Yeah.
Very nice. I think Sam had a question about Shakespeare and
yeah, I was wondering. Sorry, yeah, you quote Shakespeare quite often, both in your papers and in person, and I was wondering what you like about him. Is it particularly Shakespeare that you like? Is that the main poet that I see you quote?
Oh, Shakespeare! I thought you were saying Shakespeare. Shakespeare, yes, no, good change. I guess he just is I think everybody would say Shakespeare as a dramatist is unique. I think he has plenty of people who you could say are equal to him as poets, but nobody matches him as a dramatist. I mean, just the sheer worldwide. I think the person who comes next after Shakespeare is Bertolt Brecht, way, way behind in the number of times Brecht's plays are played. And then perhaps you get this wonderful, I love the Russian, what's his name, who wrote The Cherry Orchard and 6 or so of those. You see, as I get older, my memory for names is struggling. But no, I mean the plays. So what happened was about 30 years ago, I said, before I die, I want to read every single thing that has survived of Shakespeare, and also a lot of books about him. And then the more I read, the more I think it's just incredible. He's very knowledgeable apart from anything else. And for his time, he knew a hell of a lot. He's incredibly clever, and then he comes up with this beautiful poetry and things. By the way, I must quote one thing which I love at the end of, because it's very interesting. It's connected with shape dynamics. Near the end of the Midsummer Night's Dream, Perseus is commenting on all the things that the young lovers have said in their adventures in the forest at night, and he dismisses that as he speaks about the lunatic, the lover, the poet, the lunatic, and the lover. They're all the same. You know, you can't trust anything they say. And then he talks about the poet, and he says, and as imagination bodies forth the forms of things unknown, the poet's pen turns them to shapes and gives to airy nothing a local habitation and a name. Now, there's an interesting thing about that, because you cannot translate that passage satisfactorily into any of the Latin languages, French, Italian, Spanish, because they only have the word forma. They don't have our word shape. We have the word shape because it becomes from the German, it's related to the German Gestalt, as in Gestalt psychology. And when I became aware of that only a year or two ago, I realized it's absolutely inconceivable I would have coined the expression form dynamics. There's no way that I would have talked of form dynamics. So there's something, and Shakespeare just must have felt that shape is characterizing things in some ways more precisely, more interestingly, more. There's something special about shape as opposed to form in English, and it's because we draw on both German and Latin and Greek, of course, for our vocabulary. So that's a pretty interesting fact, I think.
That's nice. Do you have any favorite books? Any favorite editions? Sorry? Of Shakespeare, do you have any? Is there a work of his that you like most, and is there a specific edition?
Well, the one that I always find that works, of the tragedies that works best in the theatre, is Hamlet. I've seen many very exciting Hamlets, although I think I would agree with most people that King Lear is probably the greatest of the tragedies. Many of the comedies I'm very fond of. I mean, I particularly like Midsummer Night's Dream and the rude mechanicals and Bottom. I mean, Bottom is. I have that. I love that quote when Bottom wakes, and he wakes and he said, "I've had a most wonderful dream. Too wonderful, past the wit of man to say what dream I had, and it shall be called Bottom's dream because it hath no bottom." I mean, that for me is sort of the infinity and wonder of the universe that is expressed there when Bottom wakes up. That's one of my very favorite passages in
Very nice.
Yes. By the way, I once was. I had some problems, and I was struggling, thinking. There's two passages in Shakespeare I must find. I just sort of suddenly something was telling me I must find these, and I couldn't think which they were. And then I after a while I realized it was those two. And there's also another lovely one about in The Tempest, where Prospero says the great globe will vanish and leave not a rack behind. That was another one that I wanted to find. But there's a few really memorable ones in Shakespeare. And of course there are, I mean, Goethe has great things in Faust as well. That individual passages, but just the breadth. I mean, what is it, 36 plays of Shakespeare, all of which are pretty good if you put them on the stage. That's no mean achievement.
So there's, as you said, there were some questions from X, from Twitter. So one of them is from David Deutsch, who says, or asks rather, what about quantum theory and Everett? Don't you find Pagewater's timelessness seductive? Isn't it compatible with your timelessness?
Yes, in many ways, because the Page and Wooter's idea sprang from the same issue, which goes back to the Wheeler-DeWitt equation, in which DeWitt tried to find a quantum theory of the whole universe and found that it would be static. The wave function of the universe would not change. One or two problems I have with Page-Wooters now, I have discussed a bit with you, Sam. One of them I know you've addressed is that the thing that you called the clock has somehow it must be read from the universe, and the original Page-Wooters paper didn't have a mechanism for that. But then there is the other question which I put to you, and I'm not sure whether you've thought much about it since then, is I don't quite see where the clock face is. I mean, a clock has two essential things. It has the moving hand, which must move over a clock face. Now, the way I think about things now is really go back to that time capsule, that the unit, it's the totality. Well, it's true within a part of the universe, but it's true of the totality of the universe, that the universe, I would say a sufficiently large part of the universe, or the whole universe, is, so to speak, it's the clock face, it's the hand of the clock. And moreover, it records the whole universe as well. It's a record of everything as well. That's what I was talking about earlier. So that's also related to my the possibility which Tim Kozlowski and myself are exploring of whether do we need any quantum mechanics at all? This is because there are probabilities for shapes which exist quite independently of any quantum mechanics. So there's a famous problem which Lewis Carroll, the author of Alice in Wonderland, Charles Dodson as a mathematician, he said, given three arbitrary triangles in a plane, in an infinite plane, what is the probability that they make an obtuse triangle? And as he posed it, he said he got the answer, but people disagreed with him, I think. As he formulated it, you've got to add some condition to make it a precise problem. And there are many different, you can find it online, quite a number of different people have come to different conclusions. But within shape dynamics, on the shape sphere, it's completely unambiguous. All you require is just the bare facts of Euclidean geometry, and essentially those three transformations, translations, rotations, and dilatations. And the answer is unambiguous. It's 3/4. And it's just the area of, so the surface area of the shape sphere is 4 pi. and it's just the fraction of the surface which is covered by points that correspond to obtuse triangles. So that's what makes me wonder whether there really is any quantum wave function and any. So the other thing, and also the Planck constant. Now the Planck constant is dimensionful, and as I said on my gravestone, it's got to be written nothing but ratios. So the Planck's constant is not in order, in my opinion. It should be emergent. I'm not denying that it's got to be emergent, but those I think it well could. In those I showed you, we saw those incredible structures that Manuel Esquerdo found. It's entirely possible, I think, that something that we could say that's what we think is the Planck constant. And also, it's worth thinking this is another paper I'm writing to be a joint paper with Tim Kozlowski. What was the evidence that that's my grandson just disappeared. What was the evidence that the founding fathers of quantum mechanics used to arrive at their theory, including all the Hilbert space structure and wave functions and things like that? Well, basically, they were trying to explain structures in photographs taken in laboratories. So what they imagined, and this was very much under the influence of de Broglie with this idea of wave functions guiding particles. So what they were assuming is before the snapshot in the laboratory is taken, the photograph, there were particles moving in space through time under the influence of an evolving wave function. And then the photograph is taken and it's captured. And that's the information from which they then try and deduce what the particles and the wave were doing. But there is, in principle, a completely different possibility for explaining that snapshot. Suppose you could take a snapshot of the whole universe, and to simplify things, let's assume that it's a huge number of particles but a finite number. And suppose that the complexity is what I call time, the value of the complexity, so that for a given those particles, there will be a huge number of them, well, an infinite number of them that have a given value of the complexity. And there will be regions there where there are types of shapes that have a high probability rather than shapes which are not so interesting. And then you could look very carefully among all those shapes, and lo and behold, in one of them, you would find exactly the snapshot taken in the laboratory, and it would give a complete explanation of the structure and the snapshot, make it redundant to call on anything. And it would all be done instantaneously, in one instant. It would all be in one single shape. So this, I think, is a perfectly logically possible alternative to quantum mechanics. Now, the question is, could you really do it all and explain them all? That, of course, is a huge task. And I'm not saying, and one of the huge problems at the moment that Tim Kozlowski and I are trying to resolve is how what role the speed of light plays in this. I'm frankly rather more confident of getting Planck's constant than the speed of light come out of this satisfactorily. But I think one has to ask these questions, and one needs to challenge them there. Anyway, so next question that you had, I think you had a few that people had put in.
Yeah, we have one more by Brett Wall. Is it feasible to go back to Newtonian gravity, given it was falsified by Eddington and many other experiments, and to Newtonian mechanics, given experiments in quantum theory refuting that?
So let me deal with the first question, then I'll ask you to repeat the second one. The first one is, I doubt very much that we just go back to Newtonian theory. There's just, I think that general relativity is I think it's entirely possible that general relativity is very poorly understood near the Big Bang, or it might actually be wrong near the Big Bang. But there's so much evidence now that it's an incredibly good theory in the modern epoch and after there. I mean, the thing that really impresses me above all is that observational evidence only a few years ago, when I think it was a neutron star merged with a black hole, and they were able to observe it both in gravitational waves and optically. And that confirmed that light and gravitational waves travel at the same speed. That's a phenomenal confirmation of Einstein's theory. So I think it's very hard to think that Newton could do that. But I think Newton might give some very, very valuable hints on trying to understand general relativity near the Big Bang, and possibly even when black holes do merge. And the second question was from Brett.
Is it feasible to go back to Newtonian mechanics, given experiments in quantum theory refuting that?
I think it might be possible to go back to something quite like Newtonian mechanics. I think the big issue that would definitely have to be resolved is this one to do with the speed of light. I mean, the speed of light, or the universal speed now, because we know it also applies. And also, we also know that you can't accelerate things faster than that, or anything faster than the speed of light. So there's a universal velocity in the universe, and there's no trace of that in Newton's theory as he created it. So to that extent, I don't think you can do everything with Newton. But what I do think you might get a lot of very valuable hints from Newton, particularly when expressed in terms, when you've got rid of all that corruption that he himself ironically brought in with his pesky absolutes.
Interesting. Well, you both have been very generous with your time. I do have one final question, and maybe Sam might have more, some final comments. But obviously, you've criticized and refuted such a fundamental concept to so many people, time. And do you ever think about how many other things that there might be out there that we just accept without question, and maybe just thinking a little critically about them could lead to important breakthroughs?
Well, I mean, one of the ideals, of course, I have it, and I'm hoping to write one last book, and I might try and put it in, is really to show how all forms of creation could be understood in this sort of way, that besides that comment that I already made about the etymology of creation, another one is the etymology of the word idea. So that comes from the Greek word for pattern. And if you think about it, everything in physics, chemistry, and all forms of art is about patterns. It's pattern structure. I mean, as in one of Shakespeare's sonnet 12, when I do count the clock that tells the time, you know, there's pattern in that. It's an iambic pentameter. And his sonnets, they have to have this specific structure. Patterns are shapes and patterns. This is. I mean, patterns is making shapes a bit more precise. There's some sort of regularity in the structure. So I would say it might be possible to. I would say this is what I'm hoping to put into a book, but if not, I've said it to you too, is that sort of the science which came out well, first from the ancient astronomers who made those marvelous discoveries coming through to Kepler, and then with Newton, and then all the stuff that's come since then. this could be, in some very deep sense, unified with what we would think of as the creative arts, painting, music, what you like.
Well, Sam, do you have any final comments? Questions?
I don't think so, no. I think it was very enlightening. It's always great speaking to you, Julian. And yeah, thanks so much for coming on.
Well, pleasure.